we replace the source term with fission term. That is the only difference between diffusion equation and reactor equation. Before we derive, we have to define some condition. So we call bare reactor bare. That means without close. So actually, bare reactor means reactor without a blanket or reflector. So just the reactor part. So it is a bare reactor. So it doesn't have a blanket or reflector. So it is bare without close, bare reactor. So we know we Godiva. What is Godiva? So this is the name of a chocolate shop, Godiva. Actually, this is a noble woman. I think she was a duchess. Uh, she rode the horse without clothes. So with she's Godiva. So look up any internet search to get the meaning of Godiva. So actually, it is not simply the title of chocolate shop. So Godiva. So in nuclear engineering, when we say bioreactor or Godiva, it means nuclear reactor without blanket or without reflector. So it is bioreactor. So you have to memorize bioreactor and Godiva as well. So look up Godiva. Now, the first equation is one group time-dependent diffusion equation. You remember, time-dependent. And the source term S is fission term. So when we multiply sigma F times flux, sigma F phi is number of fission, right? Number of fission, and we multiplied nu, that is average number of neutron born after fission. So source equals nu sigma F phi. So sigma F phi means number of fission, and nu means average number of neutron appear after fission. So source S is nu sigma F phi. We then that is original meaning of source term. So then we make some kind of manipulation to deal it easily. So what we would are aiming is we would like to replace the term sigma F with sigma A. So sigma A uh, from the definition of the 1, 2, 3, 4. Fourth equation, F equal sigma absorbed fission cross section divided by absorption cross section. That means rate of fission cross section. So F times sigma A equals sigma F, right? So and number of fission appear per absorption is eta, right? So we changed the expression source term equal eta F sigma A flux phi. Okay, so we replace the source term. Sigma A is cross section for absorption cross section for mixture and fuel and coolant, and sigma AF is cross section for fuel. Okay, so I told you we have diffusion equation, and so source term is replaced. Basically source term is number of fission times average number of neutron appear after fission. That is all S equal 2 sigma f a phi. And in order to, before we substitute this source term expression to the diffusion equation, so it is not easy to use sigma a and sigma f. So we would transform sigma f to sigma a by using thermal utilization factor f. So f, the nominator is Fisher cross-section, and the denominator is total absorption cross-section. So sigma f can be replaced by f times sigma a, and eta is replacing sigma nu, because nu is average number of neutron after fission, but eta is average number of neutron after absorption. So we replaced nu and sigma f expression, and S becomes eta f sigma a flux. Then we can substitute this equation to the diffusion equation. Or we can further do that. Eta f is a multiplication factor for infinite reactor. So we can replace eta f with k infinite. So k infinite means there is infinite reactor. So infinite in an infinite reactor there is no neutron escape. So then there is no leakage term. So we can replace eta f with k infinite. Now we substitute source term. D Laplacian phi minus sigma a phi plus k infinite sigma a phi equals this. For the steady state case, the right hand side becomes 0, and we can combine second and third term in the left hand side. Okay, we combine the second and third term in the left hand side. Then we get second equation, and we divide this equation with D, and using the definition of L, thermal diffusion area, we can change this equation. So this is the reactor equation, and we put L k infinite minus 1 divided by L square. We define this as B square, like this. So this is one group diffusion equation. This is one group diffusion equation. And B square, if we rearrange the second equation with respect to B square equals Laplacian phi divided by phi. So there is a curvature. So B, when we solve the diffusion equation, when we made a linear combination, the coefficient was A and C, not B, right? So when we solved the diffusion equation in chapter 5, we have two general solutions, phi 1 and phi 2, and then we make linear combination of that. Phi equals A phi 1 plus B phi 2. No, A phi 1 plus C phi 2. We reserved B because of this. In nuclear engineering, B is a special character reserved for buckling. So you know buckle. So if buckle is fit for the curvature, So if he or she is a fat, then buckle is flattened, and also if he or she is thin, so the buckle is have more curvature. So when we see the buckle, so then we can check the size of the reactor. So that's why we call it buckling. So uh, uh, again, buckle, like a belt in the buckle. So for the fat man, it is a little bit more flat. Thin man, it is more curved, right? So when we see the buckle, we can see how fat he or she is. So like this, when in the mathematical terms, when we rearrange the second equation with respect to B buckling, B square equals Laplacian phi divided by phi. That is the definition of curvature, right? So that is a physical meaning of buckling is curvature. So we defined B square is K infinite minus 1 divided by L square. We can do this kind of operation. We multiply both sides with L square and rearrange the second equation with respect to K infinite, and then divided by right hand side, we get this expression. So what was K infinite? K infinite was a multiplication factor for infinite reactor. Multiplication factor for infinite, right? Multiplication factor for infinite reactor. And B square is B. What was B in the reactor equation? B square replacing the Laplacian, right? So B square times L square is leakage, right? So uh, the multiplication factor has a production term at denominator and absorption and leakage term in the denominator. So one is the absorption coefficient, and B square L square denotes diffusion. So that means this equation says for the finite reactor, uh, left hand side is multiplication for the finite reactor, and it is 1 for the critical reactor. Okay, so let's again. K infinite was a multiplication factor for infinite reactor. There is no leakage. But in denominator, we have 1 plus B square L square. So B square L square is diffusion term. Look back on the reactor equation. Laplacian phi plus B square phi equals 0. Right? So well, B square representing Laplacian. So this is this can be the diffusion term. So the left hand side is K infinite is multiplication factor for infinite reactor. That means K infinite does not include leakage term, but in the denominator we have 1 plus B square L square. That B square L square denotes leakage term. So left hand side is multiplication for finite reactor, not infinite reactor. So the leakage is considered in the second term in the denominator. So left hand side is multiplication factor for finite reactor, and it is 1 in this case. Let's look the other way. So K is multiplication factor. So production term is nu sigma f phi. So that is number of fission times average neutron appear after fission. So in the denominator, dB square phi means d Laplacian phi. So minus d Laplacian phi. So the first term in the denominator is the leakage term, and second term is absorption term. So phi all cancelled out. And using the definition of thermal utilization factor F and eta, we can make the equation same as eta F over 1 plus B square L square. Again, we can make this equation, we can convert this equation eta F divided by 1 plus B square L square, like the previous pages, the last equation. So the numerator is production term and denominator is leakage and absorption term. So that is multiplication factor for finite reactor. Okay, we will learn in the next lecture how to solve the reactor equation. Okay, let's call it a day. Bye bye.
네, 나가셔도 됩니다.